Dr. Chandrasekar, Professor in the Department of Mechanical Engineering. Today we are going to discuss about engineering metrology and measurements. In this video, I am going to cover the basics of metrology. The topics I am going to cover are introduction to metrology, what is the need of metrology, what are the elements of the metrology, then what is workpiece, what is generalized measurement system, units and standards, and the major characteristics of measuring instruments, that is sensitivity, stability, range, accuracy and precision, static and dynamic response, repeatability, systematic and random errors, correction, calibration. So these are the major characteristics of measuring instruments. We are going to discuss about one by one. Then we move on to dimensional and geometric tolerance, then interchangeability. So first, the introduction to metrology. The metrology is a word derived from two Greek words. One is metro, it means measurement, and another word is logy, which means science. So metro means measurement and logy means science. So we come combining these two, metrology, that is measurements of science. So the metrology is the science of precision measurement. So the engineer can say it is the science of measurement of lengths and angles and all related quantities like width, depth, diameter and straightness with high accuracy. The development of industry largely depends on the engineering metrology. So it is irrespective of branch of engineering, all engineers should know about the various instruments and techniques used in this measurement. So definition wise, metrology is a science of measurement that includes both theoretical and practical aspects of measurement, ensuring the accuracy, precision and standardization of instruments and techniques. And we broadly classify this metrology into three categories. One is legal metrology, another one is dynamic metrology, and deterministic metrology. So first one is legal metrology. It is a part of metrology which treats units of measurements, methods of measurements and the measuring instruments in relation to technical and legal requirement. The activities of this legal metrology are control of measuring instruments, testing of prototypes or models of measuring instruments, and the examination of a measuring instrument to verify its conformity to the statutory requirements. Then next classification is dynamic metrology. Dynamic metrology is a branch of measurement science that deals with the measurement of quantities that change with the time. So which quantities are changing with the time, if you measure that quantities, they comes under dynamic metrology. It focuses on the behavior and performance of measuring instruments when the input signal is varying rapidly rather than remaining constant. So example, measurement of temperature in a jet engine, it's a very good example for dynamic metrology. Consider a thermocouple used to measure the temperature of exhaust gases in an aircraft engine. Actual gas temperature may suddenly increase from 500 degree to 800 degrees centigrade, but the thermocouple does not instantly indicate 800 degrees centigrade because its thermal inertia. Instead of measured temperature gradually rises, it reaches 800 degrees centigrade after certain time. So in this case, in this example, the input is actual gas temperature, it is changes with the time. Output is the thermocouple reading. Dynamic characteristic is time constant of thermocouple is the dynamic characteristics. The dynamic error is difference between actual and indicated temperature during transient period. So another example, automobile speedometer. When the car accelerates suddenly 40 km per hour to 80 km per hour, the actual speed changes immediately. But the speedometer needle takes a short time to reach the new value. So this is a dynamic metrology. The third one is deterministic metrology. It deals with measurements where the values of all variables affecting the measurements are known exactly, and the outcome can be predicted using deterministic equations. Example, coordinate measuring machine. The components dimension are measured using a coordinate measuring machine. Probe coordinates are measured. The software calculates the distance and geometrical features using deterministic geometric equations. Under controlled conditions, the same measurements yield the same result. This deterministic relationship between coordinates and dimensions make it a deterministic metrology application. Then objectives of metrology. First objective is complete evaluation of newly developed product. Second one is determination of process capabilities and ensure that there are better than the relevant component tolerances. Next one is determination of measuring instrument capabilities and ensure that they are quite sufficient for their respective measurements. Next objective is minimizing the cost of inspection by effective and efficient use of available facilities. The next objective is reducing the cost of rejects and rework through application of statistical quality control techniques. To standardize the measuring methods, to maintain the accuracies of measurement, and prepare designs for all cages and special inspection fixtures. The necessity and the importance of metrology. First one is need of metrology. First one is quality assurance. It ensures products meet specific dimension and performance requirement, and it helps maintain uniform product quality. Second one is it enables parts manufactured at different locations to fit and function correctly without modification. This is also called as interchangeability. Then minimize scrap, rework and material wastages through accurate measurements. It establishes common measurement standards for the industries and laboratories, and it helps monitor and control manufacturing processes to achieve desired specifications. Also, it ensures critical components meet design requirements, improving safety and operational reliability. The last one is it provides precise measurements required for research, development and innovation. Then we move to elements of metrology. The metrology consists of the following fundamental elements. One is measurement standard, measuring instrument, calibration, measurement procedure, measurement environment and measurement uncertainty. So measurement means it is a physical quantity being measured. Example, length, diameter, temperature, force, pressure, etc. The measurement standard, a reference used to define and maintain the value of quantity. Examples, standard meter, gauge blocks, calibrated weights. Measuring instrument, the device used to perform the measurement is also called measuring instrument. Example, vernier caliper, autocalorimeter, micrometer, dial indicator, coordinate measuring machines. Calibration, the process of comparing an instrument with a known standard to ensure the accuracy, that is called calibration. Measurement procedure, a systematic method followed to obtain reliable and repeatable measurements. Measurement environment, environmental conditions such as temperature, humidity, vibration and dust that may affect measurement accuracy. The last one is uncertainty, measurement uncertainty, the estimated range within which the true value of the measurement lies. So these are called elements of metrology. And methods of measurements. There are 10 methods of measurements. First one is direct method, second one is indirect method, third absolute or fundamental method, next comparative method, transposition method, coincidence method, deflection method, complementary method, contact method, contactless method. So in this slide it shows the various methods of measurements. Indirect method, the value of the required quantity is obtained by measuring other related quantities by using a formula. So example, density is equal to mass by volume. So you can measure the mass by the balance. Volume can be measured by this cylinder. So these are known value. By using this formula, density equal to mass by volume, you can find the quantity called density. So this is called indirect method. Then absolute method, absolute or fundamental method, the value of quantity is determined directly from the fundamental formula without comparing with any standard. Example, measurement of resistance are equal to rho into L by A. So L is the length, A is the area, rho is the resistivity of the material. So the R resistance can be calculated. Third one is comparative method. Unknown quantity is measured by comparing it with known standard with same quantity. Example, measurement using vernier caliper is called comparative method. Then transposition method, measurements are taken by interchanging the positions of standard and the unknown to eliminate systematic errors. So measurement using beam balance, the example for this transposition method. Fifth one is coincidence method. The value is obtained by coincidence of two scales, marks or lines. Example, vernier caliper. So the sixth division here in this figure, the sixth division of vernier scale coincides with the main scale division. So measurement equal to main scale reading plus vernier coincidence into least count. Then deflection method, the value of quantity is determined from the deflection produced in an indicating instrument. The example for this deflection method is ammeter, spring balance. These are the example for deflection method. Complementary method, the known quantity is added or adjusted to balance the unknown quantity. The value of unknown is obtained from the known quantity used. So unknown weight equal to sum of standard weights. Then contact method, the measurement is made by bringing the measuring instrument in physical contact with the object. Measurement using micro screw gauge is the example for this contact method. The spindle contacts the object to measure the diameter. Contactless method, the measurement is made without any physical contact with the object. So the example is measurement of temperature using infrared thermometer. This is a best example for contactless method. So these are called methods of measurements. Then generalized measurement system. A generalized measurement system is a conceptual model that represents a sequence of elements involved in measuring a physical quantity. The physical quantity may be a length, temperature, diameter, height, width, whatever. It describes how a measurement is sensed, processed and displayed as a useful information. This is the block diagram of generalized measurement system. First one is measurement. the physical quantity to be measured. This is the input for this whole process, whole system. Next one is primary sensing element. First element that directly senses the measurement. Second one is variable conversion element. Converts the sensed information into a more convenient form. So primary sensing element, the example for primary sensing element is Bourdon tube, thermocouple junction, diaphragm, strain gauge. These are called primary sensing element. The second stage is variable conversion element, thermocouple LVDT, that is thermocouple is converts the temperature into voltages. LVDT converts the displacement to voltage. The next stage is variable manipulation element. Modifies or process the signal without changing its nature. So example for this stage is amplifier, filter, signal conditioner, analog to digital converter. Then data transmission system transmits the signal from one location to another location. The using electrical cable, fiber optic link, wireless transmitter, we can transmit the data from one location to another location. Then data presentation element. It displays, records or stores the measured value. Example, digital display, recorder, computer, printer. Then final is output, the measured value in a usable form, that is the output. So this is the block diagram of generalized measurement system. Here the digital temperature measurement system given as an example. Here the thermometer, that is temperature, is a measurand. The thermocouple used as a primary sensing element. It sends the signals to the variable conversion element as a voltage signal. Amplifier manipulates, that is amplifies the signals received from thermocouple by using transmission cable, data transmission element, and digital display, data presentation element. So the advantages of generalized measurement system are provides a systematic approach to measurement, and it helps in analyzing instrument performance. It facilitates automation and remote monitoring. It improves measurement accuracy and reliability. It's applicable to mechanical, electrical and electronic measurements. Then next one is units and standards. A unit is a definite magnitude of a physical quantity adopted by convention and used as a reference for measurement. So example for physical units are the physical quantity length. For length, the unit is meter, the symbol is m. So unit of mass is kilogram, the symbol of this is kg, and time unit is second, so S is the symbol. So temperature, the unit and symbols are given in the table for temperature, electric current, amount of substance, luminous intensity. Then importance of units, it provides a common basis for measurement and it enables uniformity in scientific engineering practices. It also facilitates communication and comparison measurements value. Then standard. A standard is a physical representation of a unit or a reference used to establish the value of a quantity. So examples are standard gauge blocks, that is it is for length, standard weights, it is for mass, then atomic clock, this is for standard, it is a time. Characteristics of a good standard: it should be accurate and reliable, it's stable over the time, it is easily reproducible, universally accepted, it's not affected by environmental condition. Then classification of standards. You can classify the standards by international standards, primary standards, secondary standards, working standards. So first one is international standards, defined and maintained by international organizations like International Bureau of Weights and Measures, and it used as a ultimate reference code value. Then primary standards, highest accuracy standards within a country. It used to calibrate secondary standards. So example is national standard meter, national standard kilogram. Then secondary standards is calibrated against primary standards and also used in laboratories and industries. The example for secondary standards are standard gauge box. Then working standard used for routine measurements and calibration work. Regularly checked against secondary standards. So, example, vernier calipers, micrometer, shop floor gauges. Okay, this is the overall concept of units and standards. Then, key characteristics of measuring instruments. The performance of a measuring instrument is described by the following important characteristics. First one is sensitivity. It is the ability of an instrument to detect small changes in the quantity being measured. So, sensitivity is equal to change in output by change in input. For example, a thermometer whose mercury column rises 2 mm for every 1 degree centigrade increase in temperature has a sensitivity of 2 millimeter per centigrade. Then stability. Stability is the ability of an instrument to maintain its accuracy and provide the same output over a long period under the same operating conditions. For example, a digital weighing machine that gives the same reading of 50 kg for the same object being after several months is considered stable. Then range. Range is the minimum and maximum values of the quantity that an instrument can measure accurately. Example, a thermometer with a scale from minus 10 degree centigrade to 150 degree centigrade has a measuring range of minus 10 degree centigrade to 150 degree centigrade. Then accuracy. Accuracy refers the closest of the measured value to the true or actual value. Example, the actual length of a rod 100 mm. If an instrument measures 99.9 mm, the measurement is highly accurate. So the accuracy is about closest of the true value. Then precision. Precision is the ability of an instrument to produce the same reading repeatedly for the same measured quantity. Example, a weighing scale gives the following readings for the same object. In first attempt, it gives 70.20, second 70.21, third 7.20, fourth 7.20, fifth one 7.21. So readings are very close to each other, so the instrument is precise. So the precision is about consistency of repeated measurements. So accuracy versus precision. Accuracy indicates how close a measurement is to the true value. At the same time, precision indicates how close repeated measurements are to each other. A measurement can be accurate but not precise. A measurement can be precise but not accurate. The next key characteristics are static response. Static response is the behavior of an instrument when the measurement is constant or changes so slowly that dynamic effects are negligible. Example is a steel ruler measuring the length of a stationary object. So the instrument output settles to a steady value corresponding to the output. Dynamic response. The dynamic response is the ability of an instrument to follow changes in the measurement with the time. So the pressure sensor measuring rapidly changing pressure inside an engine cylinder. So this graph shows pressure versus time for actual pressure and sensor output. So good dynamic response is output follows the input with minimum lag and error. Then repeatability. Repeatability is the ability of an instrument to give the same output and when the same quantity is measured repeatedly under the identical conditions. So example, a digital micrometer used to measure the diameter of a wire 5 times. So first time it shows the reading 1.234, second times 1.235, third one 1.234, fourth one also 1.234, fifth one is 1.235. So readings are very close to each other. It is good repeatability. So systematic errors. Systematic errors are predictable errors that occur in a consistent manner and cause the measured value to be always higher and lower than the true value. The types and examples are instrumental. Due to faulty calibration or wear, the systemic errors may occur. The example, a weighing machine always shows 0.5 kg more. Environmental, due to temperature, humidity, vibration, it may happen. So systematic errors will happen. So expense of seal scale due to high temperature. The next one is observational, due to improper reading by the observer. So parallax error while reading along the meter. So this is all are called systematic errors. Next one is random errors. Random errors occur due to unpredictable variations in the measurements and cause the measured values to scattered about the true value. Example, repeated measurements of a 10 volt DC voltage. In trial number 1, the measured voltage is 10.01. Second one is 9.99. In third observation, 10.03. Fourth one is 9.98 volt. Fifth one is 10.02. Sixth one is 10. So this graph shows the relation between trial number and voltage. So readings are very randomly above and below the true value, that is 10 volt. So random errors cannot be eliminated but can be reduced by repeated measurements and statistical methods. Then correction. Correction is the known adjustment applied to a measured value to obtain a more accurate value. So corrected value equal to measured value plus correction. Example for this correction is a thermometer reads 2 degree centigrade higher than the actual temperature. So the actual temperature is 25 degrees Celsius. Measured temperature is 27 degree. Correction is minus 2.0. So corrected temperature is 25. So in calibration, calibration is the process of comparing the readings of measuring instrument with a known standard and adjusting the instrument or applying correction factors to minimize errors. The example for calibration is a pressure gauge is calibrated using standard pressure calibrator. In this table shows the measurements during the calibration. Standard pressure is in kilopascal. Pressure is 0. Gauge reading also 0. Error is 0. Correction, there is no correction. If it is 50, standard pressure is 50 kilopascal, but the gauge reading shows 49. So the error is -1. So correction should be +1. Then next is standard pressure is 100. Then cage reading is 98. So error is -2. The correction is +2. Then standard pressure is 150 megapascal. The cage reading is 148. The error is -2. The correction is +2. So these are called all called major characteristics of engineering measuring instruments. Then introduction to dimensional tolerance. Dimensional tolerance is the permissible or allowable variation in the size of component from its basic, that is nominal dimension. It defines the maximum and minimum limits within which the actual dimension of a component must lie. So here the actual dimension of the rod is 50. The upper limit, we give the dimensional tolerance. The upper limit is 50.02 millimeter. The lower limit is 49.98 millimeter. So total tolerance is upper limit minus lower limit, the 0.04 mm. So if when you measure this rod, this part, if the measurement lies between this upper limit and lower limit, we can accept this part. So what is the need for dimensional tolerance? Manufacturing process cannot produce perfectly accurate dimensions. It allows components produced by different manufacturers to fit and functions properly. It reduces manufacturing cost by avoiding unnecessary precision. It helps in maintaining quality and reliability of products. Also, it ensures interchangeability of machine parts. This table shows what are the terms used in dimensional tolerance. One is basic size, that is theoretical size from which the limits of size are determined. Then actual size, the size obtained by measuring the finished component. Then limits of size, two extreme permissible sizes. The fourth one is tolerance, the difference between upper limit and lower limit. So this is the relationship between basic size and limits and tolerance. This is the basic size 50 mm. So the lower limit is 49.98, upper limit is 50.02. So total tolerance is upper limit minus lower limit, it's a 0.04. Then types of dimensional tolerance. There are two types of dimensional tolerance. One is unilateral tolerance, second one is bilateral tolerance. The variation in dimension is permitted only in one direction from the basic size, called unilateral tolerance. Further, you can divide this unilateral tolerance into positive unilateral tolerance and negative unilateral tolerance. First one is positive unilateral tolerance. The variation allowed only above the basic size. So the basic size is 25 mm. So the variation will be allowed above the 25 mm. So the upper limit only, there is upper limit only. So the tolerance is 25 to 25.03. The negative unilateral tolerance, the variation allowed only below the basic size. So the basic size is 25 mm. The lower limit is 24.97. There is no upper limit. So bilateral tolerance, the variation in dimension is permitted in both positive and negative direction from the basic size. So already we discussed this bilateral tolerance. The importance of dimensional tolerance, it ensures proper assembly and fit between mating components and allows mass production and interchangeability and improves product quality and reliability. It reduces rejection of manufactured parts, provides economical manufacturing by avoiding unnecessary accuracy. Then geometric tolerance. Geometric tolerance is a system of symbols and rules used on engineering drawings to control the variation in shape, orientation, location and runout features of part. What is the need of geometric tolerance? Is the parts are made different process and machines always have small variations. So this geometrical tolerance controls this variation to ensure proper fit, function, interchangeability. So this slide shows the different types of geometrical tolerance. One is form tolerance, that is straightness, flatness, circularity, cylindricity. Then orientation tolerance, parallelism, perpendicularity, angularity. In location tolerance, position, concentricity, symmetry. Runout tolerance is circular runout, total runout. Then interchangeability. The interchangeability is the ability of one component to replace another component in an assembly and perform the same function without any modification or special fitting. In simple words, any part produced within the specified limit can be interchanged with another part of same specification and assembly will function properly. So this is called interchangeability. What is the need of interchangeability is to assemble the parts quickly and easily, reduce manufacturing cost, to facilitate mass production and simplify the inspection and assembly process and ensures availability of parts. So the application benefits of interchangeability are quick and easy assembly, reduction in production time and cost, uniform quality of measurements, products, easy replacement of worn and damaged parts, facilitate mass production and standardization. The application of interchangeabilities are the interchangeability used in automobiles, machines, electrical appliances and consumer products, bearing, bolts, nuts, gears, shaft, piston rings, etc. are manufactured with standard tolerance to ensure interchangeability. So far we discussed the basics of engineering metrology and measurements. Thank you.